Yeah, so today we will have 2 lectures on Markov decision processes. So we take a Markov chain and we extend it by non-determinism. That's the way you can think of a Markov decision process. Well, when I started to work in this area, which is now more than 20 years ago, there was a bit discussion, why do we need, if you have probabilism, why do you need non-determinism? And the answer is very simple. If you want to describe the behavior of a distributed system by interleaving and not using some kind of Petrinet model, then you need the non-determinism to describe this interleaving behavior. Well, and this one here is the typical picture. You are in a certain state S, and 2 processes toss a coin independently, and then instead of having this classical interleaving diamond in the purely non-deterministic case, we have a picture like this. So either the first process goes on and then followed by the second process, or the other way around. In either case, each of the possible 4 outcomes, head, tail, and so on, they will occur with the same probability, 1/4 in either case. Well, there are also other reasons why the non-determinism is a crucial feature. So it is the key for almost every abstraction technique for probabilistic systems, and as it is known from non-probabilistic systems, it is also the standard thing. If you don't know anything about the environment, let's say a human user, and you do not have any stochastic assumptions, then the best thing you can do is to describe it in a non-deterministic way. So let's say the picture you should keep in mind for a Markov decision process is we combine the concept of transition systems, a purely non-deterministic model, where in this context we consider the choice between 2 actions as a non-deterministic choice without any probabilities, and here the Markov chain, that's the purely probabilistic setting. Combining this results in a picture like this. You are in a state, then you have a non-deterministic choice to pick one of the enabled actions, and for each of them you have a distribution for the successor states.
But you made a switch from nondeterminism to Markov decision process, and it's important to point out that in the classical operation research literature, you control the non-determinism,
Yeah,
and the adversary behaves probabilistically.
yeah, that's right.
Here we switch it.
Yeah,
right?
that's right. Yeah, that's right. Well, and you can attach integer weights or natural numbers as weights either to the states or what I will do here to the state action pairs. Now, formally, we have in our case we consider only finite Markov decision processes, which means the state space is finite, and so is the set of actions. And this picture here, we formalize it by a function that P that takes as argument the current state plus the action you have chosen, and then depending on what is the target state, it returns a probability value. Well, and as I said, you can attach rewards or weight functions, let's say energy utility, cost utility, and they can be either natural numbers or integer values. I will come back to this later. Well, now the crucial thing is in a Markov chain, we defined what is the probability. Now here in this Markov decision process, we can do an analogous thing, but things become a bit more difficult because of the non-determinism. And speaking roughly, it makes little sense to talk about probabilities unless the non-determinism has been resolved. And we do this by taking a scheduler, which simply means a function that takes the history of the system as input, so given the finite paths that had been taken so far, and then it returns a distribution over the possible actions that can be taken in the current state. So, and well, for this is just a definition of a function. I do not say anything about computability or so. And having such a scheduler can be a very strange function. You can unfold the behavior of an MDP into a tree-like infinite state Markov chain, and then you can rely on classical concepts of measure and probability theory to define the probability measure. Well, I don't have a slide for this, just use your intuition, but you get an infinite Markov chain, and the concepts are the same as I've shown you. Well, I said I assume that the Markov chain is finite, but the definition of the probability measure would be the same. Well, you can classify the schedulers in various dimensions by saying that given a path, a finite path, then a scheduler returns a distribution over the actions. This would be a randomized scheduler, and the case of a deterministic one is just one that returns a unique action. So probability 1 for one specific action and probability 0 for the others. Well, and then another dimension to classify schedulers is according to their memory requirements. So instead of saying the input is just a finite path, you can describe the behavior of a scheduler using some set of memory cells. And then there is a memory update function, what I called here new, depending on the current state, and the decision function, what I called here mu, which takes the current memory cell plus the current state and returns a distribution over the actions. Now, if you do not make any restrictions on the set of memory cells, you might deal with the finite paths, in which case you get the full class of schedulers. So this is H for history dependent. Finite memory simply means that the set of memory cells is finite, and memoryless simply means that you have a single memory cell or you have no information at all.
Why do we need finite memory? Since if the memory is finite, we can always encode this finite memory in terms of the state. So we will still have stateless, memoryless Markov computing process.
Sorry,
I mean, if we only have finite memory, then we can always encode those information onto state. Right?
I don't know, I'm talking here about the schedulers.
Yeah, I mean, so we have
well, but a finite memory scheduler, it might switch. So let's say if you go any second time you visit a state, it might switch between actions alpha and beta, might alternate. That's not memoryless behavior. So there is a difference. Well, in the end, for the properties, we'll talk about the class of deterministic and finite memory schedulers will be sufficient, but we come to this later. Well, let's start with a simple example. Let's take trivial mutual exclusion protocol for two processes called P1, P2, and we describe each of them just by 3 locations. Ni means the non-critical phase of process Pi, Wi means the phase or the location where Pi is after having requested to enter the critical section, and Ci means that process Pi performs its critical activities. So if both are waiting, we suppose we have a competition and only one of them may enter the critical section. And let's look here for a trivial protocol using a randomized arbiter who simply tosses a coin to decide which of the processes may enter. Now the full MDP looks like this. So altogether we will have 8 reachable states. And when I dropped here any probability notation, I mean performance with probability 1. So, for instance, if both are waiting, then we have here the classical interleaving diamond known from non-probabilistic systems, simply because the processes may perform the request operation completely independently, and so no matter which order you choose, we will end up in this state where both are waiting. Well, in this state we have the competition, and for this trivial protocol we suppose that there is some other process who tosses a coin, and so with probability 1/2 the first process or the second process may enter. So let's look now for some properties. First, the classical mutual exclusion safety property, stating correctness in the sense that the processes are never simultaneously in their critical section, and for this one this has nothing to do with probabilities.
What does it mean here, never? With probability 0 or exactly never?
Exactly never, because on all passes you will never see a state where both are in their critical section. This is simply not, well, you could add this state, but it is not reachable. Now, each liveness in the sense of each waiting process will eventually enter its critical section. If you would use techniques that are known for non-probabilistic systems, then the answer would be no, because there are behaviors, for instance this one here, where it is only the first process who runs through its 3 phases at infinity, while the second process is waiting ad infinity. However, well, intuitively this property holds, this liveness property, but it does not hold on all passes, but on almost all passes, which means with probability 1, no matter which scheduler you choose. Now suppose the second process is waiting, which means we are in one of these three states here. If you ask what is the probability that the process 2, the second process, enters its critical section within 3 or fewer steps, then, well, as I said before, it makes no sense to talk about probabilities without resolving the non-determinism 4, so there is no serious answer for that. So look, for instance, for that state, the first process is in its non-critical phase and the second one is waiting. Then in case that we deal with a scheduler where first the first process moves on and performs its request operation, then there is a probability 1/2 for the second process to enter its critical section within 3 or fewer steps. While on the other hand, if the scheduler chooses directly this enter 2 action where the second process moves directly to its critical section, then the probability would be 1. Which means that what is the probability for process 2 to enter its critical section? It depends on the scheduler. Now here's the picture, the probabilistic model checking picture. Here on the left-hand side, we assume that we have modeled our system using a Markov decision process, and assume here on the left-hand side we have specified some properties using path properties using LTL formulas. Then, well, because there is no unique answer for probability for formula phi, the typical thing what one does is a best or worst case analysis, which means we take the extremum over the probabilities when ranging over all the schedulers. So we look for the per min or per max. Well, I wrote here min and max at this stage. It's not the class of schedulers is infinite, so it could be a sub or a supremum or infimum. But indeed, for LTL formulas, this is a proper min and a proper max. And it is known that the class of deterministic finite memory schedulers is sufficient to achieve this minimum or this maximum. Well, and to continue with this picture, you have seen a very analogous picture for Markov chains. So what we do is we translate this given LTL formula into a deterministic automaton. And indeed, on some slides that will come later, we will use here a deterministic Rabin automaton, so as you have heard in Javier's talk. And then the remaining steps are very similar as you have seen for Markov chains. So we glue together the MDP plus this deterministic automaton and build a new Markov decision process, which results by running them in parallel. And then the question to compute the min or the max probability, it will be reduced to a reachability probability, to the maximal reachability property in case we deal here with the max. And to reach, well, remind what we did in the case for Markov chains, we looked for the good bottom strongly connected components, and good means that the acceptance condition of the automaton is satisfied. And the analogous thing here in the case of an MDP, these are the so-called end components, and we check here which of them fulfills the acceptance condition of this automaton. So let's start with this notion of an end component, which can be understood as the MDP analog to a bottom strongly connected component. So, maybe the simplest definition of an end component would be it is a strongly connected sub-MDP. So you can formalize it as a pair consisting of a non-empty set of states plus a function that assigns to each state in T a set of actions such that indeed it's a proper choice of the action, so which means if you choose some action alpha for state T, then T should indeed be able to execute this action. It should be closed under probabilistic branching, which means that indeed we want to get a sub-MDP, so any probabilistic branch when taking action alpha in state T should lead to a state which again belongs to T. And if you just look for the underlying graph structure, then it should be strongly connected. Well, and instead of this TA, you can also consider this as state action pairs. That's just another view on these MDPs. Well, satisfying these constraints, being strongly connected and inducing a sub-MDP. Yeah, so look at this picture here. That's an MDP, and only these actions alpha, only these violet actions and this action beta here are the probabilistic ones. The other ones are all deterministic in the sense they have a unique successor state. So I omit here to attach probability 1. So here, for instance, we have such an end component, a strongly connected sub-MDP, and for this state here, the actions, we just take action delta and this action sigma, but not the beta, because with one feed we leave this area. Well, and this one here is also an end component. And please note that end components can contain subcomponents, so we do not say that they need to be maximal. So for instance here, these two states together with actions delta and gamma, they also constitute an end component. Now for Markov chains, I mentioned this fundamental property stating for finite state Markov chains that almost surely with probability 1 we will reach a bottom strongly connected component, stay there forever, and visit all its states infinitely often. Now the analogous statement in an MDP is no matter which scheduler you choose, it might be a very strange one, even not computable, what we can guarantee is that almost all infinite passes will eventually enter an end component, stay there forever, and visit all its states infinitely often. This for different passes, let's say given a scheduler, then different passes might visit different end components. But anyway, this holds, yeah.
How can we mix the probabilistic and the transition with, I mean, so here we have data that have probability 3 of 8, and the probability of staying in the same state is 5 of 8, and what it its probability is 1 in total. So it is not it's not possible to get to other state.
From this state,
yes.
Well, if, let's say you take this loop with probability 5 over 8, and then the scheduler might tell you, now I take delta. Or it might tell you, take beta again.
But the total with beta and the looping in the same state is probability 1, right?
Well, if you consider the scheduler which for this state only takes action beta, then with probability 1 it will take this transition on the long run. Yeah.
You define it what is subcomponent or end component, yes?
Yeah.
And there, if I'm looking to action, yes, on every action there are probability. The sum is not maybe less than 1. So this is okay, yes?
No, this is not the case. The sum must be 1.
Even in
I said that it is closed, an end component must be closed under probabilistic branching, which means whatever action you take inside an end component, that's built in of the definition of an end component, then for any probabilistic branch you will stay in this end component. So indeed, wait a second, this state together with action beta does not belong to any end component.
But there is beta which is going from this state to itself. This probability.
They belong together. I'm sorry, they belong together. I should have written here beta as well. This is the same beta. I'm sorry for that.
So this beta is not present in the subcomponent.
No, and even not contained in any end component. Okay, so let's look now. Well, let's take a Rabin condition. Well, you can assume that in this model tracking picture, you started with an MDP, you started with an LTL formula, you translated the LTL formula into a deterministic Rabin automaton, and when taking the product, then we consider some Rabin condition for the product. So, and that this Rabin condition, I called it here E. I think Javier used the letters F and G, if you remind well. I use here letters L and U and used LTL notations. So the way to read this Rabin condition is with this disjunction, there should be at least one Rabin pair, Li-Ui, such that from some moment on we do not visit any state in Li, but we visit infinitely often the set Ui. So let's look now for the maximal probability in the given MDP to satisfy this Rabin condition. Then this is the maximal probability from the same state to visit eventually an accepting end component. And here accepting means now the following, or accepting end component. This means the set of all states that belong to some end component where, well, E is satisfied in the sense that there is at least one Rabin pair, Li-Ui, where Ti does not contain any Li state, but it intersects with Ui. So when staying forever in this end component T, then you will never see a state in Li, which means that the left-hand side here is fulfilled, and you will visit, well, with this visiting infinitely often any state inside T, we make sure that we will hit Ui infinitely often. Well, now as I mentioned this, we do not say that the end components need to be maximal, and so the number of end components can be exponential in the same way as the numbers of cycles in a graph can be exponential. However, we can switch to maximal end components, and this maximality simply means that there is no other end component that strictly subsumes the given end component. So you cannot extend it by states or actions. And then the set of maximal end components, this is bounded by the number of state action pairs. Yeah.
So you say that the probability to meet the Rabin condition is the probability to reach an accepting end component.
Yeah.
But when you reach an accepting end component, you can go out of it with an action.
Yeah, that's right. But I took here the max, which means that for an end component, there is, by definition, there is always a scheduler which forces you to realize exactly this end component. So you're completely right. If you pick an arbitrary scheduler, if I would have claimed that this equality holds for an arbitrary scheduler, it would be wrong. But I have here the max, which means you enter this end component, the good one, and then there is a scheduler which realizes this end component and visits all its states infinitely often and no other states. And so with the max, it's fine. But for the same thing with an arbitrary scheduler might be wrong. That's right.
Now this is a scheduler with memory.
And this is a scheduler with memory. Right. Right. Now I switched here to maximal end components, but this needs a mild trick. So we look here for the maximal end, we look for these Rabin pairs separately. And for each of them, we look for the MDP that results by removing all the states in Li. And then we look for the maximal end components in this new sub-MDP, which is a sub-MDP of M. And then we check which of these maximal end components intersect with Ui. And this is the way we make sure the first part by removing the Li states, and this second part we want to visit Ui infinitely often. We get it by looking for the maximal end components that intersect with Ui. Well, and this, I will come to this in a second. The maximal end components can be computed efficiently. I will come to this in a second. And there is also an analogous approach for generalized Rabin conditions. Javier mentioned this also. So here we have, I wrote it here in that form, we have a big disjunction, but now not over Rabin pairs, but Rabin tuples, if you want. So we still have a constraint not to visit some set Li from some moment on, but then we have here a generalized Büchi condition that we can require to visit some sets infinitely often. Yeah?
The question, if you take the Rabin condition and say the probability to the maximum probability equals the maximum probability reaching and accepting n component, because there can be a scheduler realizing
Yeah.
it. But now you say maximal n component, then can't there be a better scheduler because we don't allow to visit the Li states infinitely often, so there might be a subcomponent in which this
Well, that's a theorem stating that this is not the case.
Okay, so that's nothing. Okay.
It is complete. This is right. There is a
Go
theorem.
back to the theorem. Go back to the theorem. You had a theorem with n components.
This one here.
No, I think before that there was a theorem example. You had a big theorem. The theorem that says that you can just reduce the analysis of MDPs to the
Yeah.
analysis of
Well, I had just this picture.
picture.
But it states the same as here. Well, this is a theorem that this equality holds. There is no better. So and that's not approximate. That's really an equality.
Okay, I can accept that, but I don't see it.
Can you give some
It-
intuition why this is the case?
Well, indeed, the crucial point is exactly this one here. You just need to think about the passes that eventually realize some end component. And so it must be, for the maximal probability, let's say, then just save the good ones.
Take an arbitrary scheduler. Once you multiply, take an arbitrary scheduler. Once you multiply with a Markov chain, you will get a bigger Markov chain, but its bottom component will correspond to n components. That's the point.
Yeah.
You take arbitrary scheduler by infinite set machine. You take the product with the MDP, and then you get a Markov chain. And this Markov chain will have n components, bottom components, and they will correspond to the n component.
Yeah, to the n component, but not to the maximum
So
n
the-
component.
Yeah, they will be, and the
Yeah.
probability only gets larger in a bigger component.
But you mean this switch here? You mean this equality? Well, this equality is because I removed here the Li states. I just want to compute to get an efficient characterization or efficiently computable characterization of this set, what I called here AC. And this one is the same as this one here, taking the big union of the maximal end components in these modified MDPs with the side constraint that T does intersect with UI. The point of this equality is just how to compute this with this characterization over all end components, considering all end components would be a method, but there could be exponentially many. And
We were in the original NDP. Then I thought maybe there could be a maximum subcomponent without
but-
Li, but you removed the states.
yeah.
Yeah.
Okay, so which means this is a summary of the steps. Model checking or computing this maximal probability for a Rabin condition. We need algorithms to compute the maximal end components in these modified ones. Then we check which of them fulfills E, so this is just checking this intersection condition. And the last step, well, computing how to compute this value here. Now first, computing maximal end components, as I said, this can be done efficiently in polynomial time, and what is there are quite good algorithms. This one here, this sketches a quadratic one. So run standard algorithms to compute the strongly connected components in your MDP viewed as a graph, directed graph. Then you can, in each of these SEC, check which of the states action pairs leave the corresponding SEC. If so, then they cannot be contained in any maximal end component, just remove them. And you iterate. Then you get a new graph. You can run again an algorithm to compute the strongly connected components. And you iterate this process until it stabilizes, and in which case the resulting strongly connected components are indeed the maximal end components. And one side remark, you can use this technique also to build the so-called MEC quotient. The idea is to collapse all states that belong to the same maximal end component into a single state. What you get is a new MDP. The size is obviously bounded by the size of the original MDP, which has no end components anymore, which means that it almost, under each scheduler, it almost surely reaches a trap, by which I mean a state without any enabled actions. And this MEC quotient preserves the maximal or minimal reachability probabilities, assuming for the min probabilities, assuming that the reachability, the good states or the set of states you want to reach does not belong to the considered maximal end component. Well, then this checking which of these maximal end components fulfills E, this is just checking this intersection condition. This is trivial. And let's look now how to compute the maximal reachability probabilities. And remind, so without this maximal in Markov chains, we dealt with linear equation systems. The corresponding thing here are linear programs. So let's have a closer look at that. So suppose we are given an MDPM. The state space is S, and there are certain states, a set of states G that we want to reach. So let's XS denote the maximal probability to reach G from this particular state S. Now the first observation is, take this vector consisting of these maximal reachability probabilities. That's a vector with entries between 0 and 1. The first observation is this vector is the least solution of this equation system here. XS is 1 if S is a goal state. And otherwise, we take the max over all the actions that you can take in state S. And from then on, that's, well, what you know from Markov chains. We take the transition probability to move from S via alpha to some state T, and we multiplied it with the maximal probability to reach G from state T, and we sum up here over all states T.
What do you mean by the least solution?
Least, well, component-wise with respect to the natural order. Component-wise.
Taking some LP.
No, just component-wise. Well, you could add the constraint XS equals 0 if S has not a path reaching G. If S cannot reach G at all. And these states, of course, can be determined using a standard reachability analysis. Well, these ones here are called the Bellman equations. And let's have a closer look. So far, I just said least solution. There are several observations on this. First, this one here induces, these Bellman equations induce an optimal memoryless deterministic scheduler, and by optimal I mean one that maximizes the probability to reach G from every state. Well, and how to get this? Well, for a state in G you can take any action, and the same here in case that XS is 0, pick an arbitrary action. And for this, if this does not apply, then for each such state pick one of these, pick an argmax, so pick one of these actions where this sum is indeed maximal. Well, and instead here I said S in G, you can do a pre-analysis just using graph algorithms to filter out all the states where XS is 1. This, I will not explain this here. Okay, now so far we had least solution. We get a unique solution in case that M has no end components at all. Well, in this case, if M has no end components at all, then, well, this is called the contracting case. well, the probability matrix, it's not a quadratic matrix, but given some memoryless scheduler, then memoryless or arbitrary memoryless scheduler, then you get a classical matrix, quadratic matrix with one row and column for each state. And this matrix enjoys the property that it is contracting in the sense that with probability 1, you will reach one of the trap states. This is, if you do not have end components, then this is the case. So in this case, we have a unique solution. And in this case...
I mean, the whole MDP is not an end component?
No, yeah, well, it can be, but it need not to be. You can, well, I allow for traps, states where you do not have any outgoing transitions.
Especially when it's not strongly connected.
Yeah, yeah. Well, in this case, convergence of this value iterations, or you just do the naive thing, you start here for these values, for these states with value 1 and 0, and for these values, you can start with an arbitrary value. Convergence is ensured, convergence is ensured. It's the limit for any starting value. This also works if you have end components and you start for these ones here in this case, for these states with some value which is lower than the wanted probability vector. And it also works if you start with your starting vector contains values which are all greater or equal than the maximal reachability probabilities. But what about the termination condition in the general case, which means you iterate this, and if you want to guarantee epsilon precision, when should you stop? Well, indeed, there are some kind of formulas, but there is a very elegant approach that has been proposed by Haddad and Momesh. They proposed a value iteration which uses two sequences. One converges from below and the other one converges from above, and you just can check whether these values, for each state S, if the difference is bounded by epsilon, then you're on the safe side. Well, and I mentioned that so far we have some iterative approach to compute some approximate solution, and to get the precise values, you can, instead of having here the max, xs equals the max over all actions that you can take in state alpha, you can replace it here with some inequality. Xs is at least is greater or equal than this value here for each of the actions that you can take in state S. Well, this gives you some linear constraints, and to get a unique solution, you can add the constraint that all the xs should be minimal, and in this case, this is the same as the sum of the xs should be minimal. Well, and this gives you a polynomial time algorithm to compute the precise values of these maximal reachability probabilities. Yeah, well, here's just to illustrate this least versus unique solution. So we want to reach the goal state here, so this is our good state. And if you just look for the Bellman equations, then for this state here, tau with probability 1, we would get the equation xu equals xu, which obviously has no unique solution. But least solution, and indeed u cannot reach the goal state at all, so this value is certainly 0. And here for state X, for the state S, we have two options: either take beta or take this action alpha, which gives us the max over, well, if we take beta, then we just get xs equals xt. And if we take action alpha, then we just get the value 1/2. And for t, we just have this option to move directly to state S, which gives us this equation. Well, and again, this one here, there are many solutions. The only constraint is that xt and xs are the same, and they should be that they are bounded below by 1/2. Well, but again, the least solution of this, the least solution is obviously that both have the value 1/2. And I mentioned this MEC quotient. In this case, we have just a single, well, we have two end components. This one is an end component as well, but this one is also an end component. If you collapse them, these states, then you get this one here is the MEC quotient. And in this case, there is a unique solution for that state, this combined state. The probability would be just 1/2, the result we wanted to have. Yeah, so let's talk now about what is called stochastic, typically shortest path problem. Indeed, I will look for the stochastic longest path problem. So expectations, and remind this symbol here. I think on the next slide I have the explanation again. So I used this diamond with plus to indicate the random variable that takes as input an infinite path or maximal path and returns the accumulated reward or weight for the shortest prefix and shortest according to the condition until we reach the goal state. And then we take this E stands for expectation, and then depending on the scheduler, we have for different scheduler you can have different expectations. So we look here for the min or for the maximal expectation. Well, now these expectations, they might not exist, and the simplest way to ensure the existence of minimal or maximal expectations is to impose the requirement that the goal state will be reached almost surely no matter which scheduler you choose, which means that the minimal probability to reach the goal state is 1. Let's look first for this case, and let's check how we can compute the maximal expectation. So here is again this definition of this random variable. You have seen it already yesterday. So, and now we have an analogous thing, this Bellman equation, as you have just seen for the maximal reachability probabilities. The vector consisting of these maximal expectations is the unique solution of this equation system. So for any state S in G, we have x as is 0 because we are already there. So the shortest prefix to reach the goal, namely G, has the accumulated weight 0. And for all other states not belonging to G, we look for the best action that you can take in that state S, which means we take here the max over all possible actions alpha. Then when firing this action alpha, we get what we earn here is the weight of the state action pair S alpha plus, and now comes here the weighted sum over all the successors T multiplied with the optimal expectation from state T. Now, with this assumption that we reach G with probability 1 from every state, this guarantees that suppose that these G states are traps, so they do not have any outgoing transition. Then indeed we have this contraction property, and the whole thing here, it can be rewritten as a fixed point equation, and this fixed point operator according, let's say, this vector space here is a Banach space. So we have a contracting map, and this gives us the existence of a unique fixed point. And again, this Bellman equation here induces an optimal memoryless deterministic scheduler simply by picking optimal actions here that maximize this sum here for each of the states not belonging to G. And for the G states, you can choose everything. Yeah?
Delta diamond G maps to R. What is the range of the random variable diamond G? In the expectation? Yeah. Is it R?
The rationals, or in this case, the way I defined it, the integers. Well, if the weights are integer weights, then we sum up we only consider some finite sums, and finite sums of rationals or integers are integers.
And as the sigma algebra, you just take the power set?
Well, the sigma algebra, by taking here the max, I look for all schedulers. Now, for each scheduler, you can unfold the behavior into a Markov chain, And there we have this standard construction, the standard sigma algebra with the cylinder sets. Yeah? Well, you can have the value iteration as you have seen for maximal reachability probabilities. And in this case, again, this is a very strong condition. It ensures convergence from every starting vector. So the limit indeed, so if you take the limit of these values here and start with the G states with value 0, then convergence is ensured everywhere. And there is also a lower and upper value iteration. This also exists in this case. Well, and again, you can rephrase the whole thing as a linear program. So instead of taking here xs equals the max over all the possible actions, you can write xs is greater or equal than the same thing here. And to make sure that we get here the same effect equals the max, we minimize all these values xs. And in this case, this is the same as minimizing the sum of the values xs. Okay, so these were the basic principles, computing maximal reachability probabilities and computing maximal or minimal expectations until reaching a goal. So let's briefly summarize this PCTL star model checking. The syntax doesn't change compared to Markov chains. We have exactly the same syntax. And on the semantic level, we do the expected thing. So for this, the only thing that need to be adapted is the semantics of the probability operator. And we use here the interpretation that this pi phi asserts that no matter which scheduler you choose, then the probability for phi will belong to the probability interval I. Now, if we deal here with a probability bound, let's say an interval 0 p, including p, then S satisfies this formula. If for all schedulers sigma, the probability for phi from state S is bounded by p. And this is the same as the maximal probability from state S is bounded by p. And you can do this also for other probability bounds. Now, concerning the PCTL or PCTL star model checking procedure, you can keep the schema as I've shown you for Markov chains. It is fairly the same, except that we need to compute these maximal probabilities for path formulas instead of just probabilities in the case of Markov chains. So going back to this picture you have seen, then if you start with a PCTL star path formula, we evaluate inner formulas first, which means that indeed we can then step to an LTL formula, and then the remaining steps are as indicated here on this slide. And as I explained to you how to deal with this Rabin automaton, we have this reduction to a maximal reachability probabilities. Now, concerning the complexity, here the first row is for Markov chains. We have this for PCTL, we have polynomial time, and with these linear programs, in the case of Markov decision processes, if we restrict to this fragment, to the PCTL fragment, we get here polynomial time as well. In the case we deal with the full LTL fragment on the path formula level, we have double exponential time completeness for Markov decision processes and p-space completeness in the case of Markov chains. Okay, so how much time do I have? 10 minutes?
10 minutes.
Okay, so let's talk now about long-run mean payoff. This is just to remind what you have seen yesterday. So take an infinite sequence or an infinite path in a weighted graph, then you can define the mean payoff or the long-run average either using the lim sub or the lim inf, and they might not be the same. However, as I mentioned, or as I showed you yesterday, in finite Markov chains, concerning the expectation, it makes no difference whether you deal with the lim inf or the lim sub. And for finite Markov decision processes, we have the same phenomenon. That's what I'm going to explain now. the maximal or minimal mean pair off, then it doesn't play any role whether you deal with lim inf or lim sub. And in the case of finite MDPs, optimal memoryless deterministic schedulers exist. And optimal means here those that maximize or minimize the mean pair off. So let's have a closer look, and let's remind first what you learned about Markov chains. Here, the computation of mean pair off, expected mean pair off, was rather simple. So in the end, the result was this one. If you want to compute the expected mean pair off from some state S0 in a finite Markov chain, then you need to determine all the bottom strongly connected components. You need linear equation systems to compute the probabilities for reaching B, each of these B SCCs from the particular state S0. And you multiply these values with the mean pair off inside some bottom strongly connected component. And for these bottom strongly connected components, the expected mean pair off does not depend on the starting state. All states have the same expected mean pair off. And this one is obtained by taking it is here, the sum of all states in B. Then we take the steady state probability or the long run frequency for being in state S, multiplied with the weight of state S. And these steady state probabilities or long run frequencies in strongly connected Markov chains, they are computable using these balance equations, which gives us a linear equation system as well. So let's look now for the corresponding thing in Markov decision processes. So let's look for the case where we attempt to maximize the expected mean pair off. Yeah, well, first here is a list of results from the literature. Optimal, maximal, memoryless deterministic schedulers exist, and they are computable in polynomial time using linear programming techniques. But now it's a different type of linear program. I show you in a second. And this, I will not zoom into these details. They are also value or policy iteration algorithms, and there are also extensions how to deal with multiple mean pair off constraints. So let's have a closer look at this, how to compute the maximal expected mean pair off. So we use now also a linear programming technique, but different from these Bellman equations, we use now variables for all state action pairs as alpha. And these variables, I called them XS alpha. And they serve to encode the long run frequencies of the state action pair as alpha under some good, well, in the end, maximal, memoryless randomized scheduler. Then, given these values, just these values here, we will obtain a corresponding memoryless randomized scheduler by doing the following. We define XS for each state simply by taking the sum over all these values XS alpha. And for those states where this value is positive, we define a randomized memoryless scheduler in such a way we say the scheduler for state S, it assigns this value here, XS alpha divided by XS, as the probability for choosing action alpha in state S. And if XS is 0, then state S doesn't play any role on the long run. It will, under this MR scheduler, it will not occur in a bottom strongly connected component of that MR scheduler. Now let's look for this linear program. In the end, the goal function, the objective of this linear program, is to maximize the sum over all state action pairs as alpha. Then we take this variable for the long run frequency, XS alpha, and we multiply it with the weight for the state action pair as alpha. And this value here is indeed the mean pair off under this MR scheduler sigma given by the constraints I just have shown you. Now we come to the constraints. Remind the steady state probabilities or the long run frequencies in a Markov chain. We use this balance equation. What flows out flows in. And here we have the analogous thing. So xt, that's the global probability mass which flows out of state T. And now here on the right-hand side, we look what flows in. So we look for all state action pairs as alpha. We take their long-run frequencies. This is this variable x as alpha. And we multiply it with the transition probability of moving from state S via alpha to state T. And we do this equation, we have it for every state T. Well, I think I forgot to say that we first look for the case where the MDP is strongly connected. I'm sorry, I forgot this to say. The next constraint is that all these long-run frequencies, they are non-negative. And finally, they should constitute a distribution, which means that if we take the sum over all these values x as alpha, then this should be 1. Well, and the result of this, so let's say this value here, is then indeed the maximal expected mean payoff. That's a result by Ludwig Kallenberg. At least I think so, that it goes back to him. Maybe you... Well, what is clear that each solution of this linear program induces an optimal MR scheduler, optimal, according to this constraint, maximize the expected mean payoff. Well, and the way to obtain this MR scheduler is, as I've shown you, pick those states where these values here are positive, and then you can define the probabilities to pick actions in these states, and for the other ones, pick arbitrary values.
But you first have to prove that the optimal scheduler is an MR scheduler.
Yeah, that's this needs a proof. That's absolutely right. Well, now the next question is, I mentioned before that there are even optimal memoryless deterministic schedulers, and it's easy to obtain them. Just pick for every state where this XS, the sum of these long-run frequencies over all the state action pairs S alpha is positive, and pick one of these actions where X S alpha is positive, and then assign this action to state S. Well, what is the ratio why this works? The optimal MR schedulers, they might have several bottom strongly connected components. But in each, because we maximize the expected mean payoff, this means each of these BSCCs has the same expected mean payoff, otherwise it would not be optimal. And that's the reason why you can, let's say, the idea behind this one here is just pick one of these BSCCs, and then this does the job. Now, this was the case where the MDP is strongly connected. Now, in the general case, so we are given still a finite MDP and without trap states. So let's suppose that there are no states that do not have any outgoing transition. How to find a scheduler that maximizes the expected mean payoffs? There are two ways. One way, and this one goes back to Kallenberg, use a linear program with two variables, the XS alpha for the long run part, the long run frequencies, as you have seen before, plus analogous variables for the transient part with analogous balance equations, and then you can combine them in some clever way. So you get one big transition, linear program with these types of variables. The other method, which I personally found a bit simpler, is consider the strongly connected components separately, compute the maximal expected mean payoff there, and then combine it, compose the result for the full MDP using some tricks, which I would have on the next slide, but I see that I need to stop. Thank you.